Yeah, good morning to one and all. Today we are going to discuss about our CO2 topics in subject Advanced Design of Reinforced Concrete Structures with course code 21 CE 3221. Myself Y. Himmat Kumar from Department of Civil Engineering. I am coming under cohort T28 Structural Engineering. So our today's topic is about pile foundations and deep beams. So coming for what are the syllabus that we are going to cover in the case of deep beams is, first we will be seeing what are the general features of the deep beams and what are the parameters that are influencing the design of deep beams, and flexural bending stress, shear stress in deep beams. So what are the IS code provisions for deep beams and design examples. Along with that, precast construction, in that introduction to precast construction, precast techniques, material properties, design concept and design considerations, precast limitations, design of composite precast precast components. So this is the syllabus that we are going to cover in our CO2. So coming for what is the meant by definition of the deep beam. The term deep beam is defined in ACI code, that is American Concrete Institute code, as the member loaded on one face and supported on opposite face so that compression struts can develop between the loads and supports, and they may be having either clear spans that are equal to or less than 4 times the overall height of the beam, or the regions located with concentrated loads with 2h from the face of the support. So as per ACI code, the term deep beam is defined as the member loaded on one face and supported on opposite face so that the compression struts can be developed between the loads and the supports. This is the definition of the deep beam as per the ACI code. And you can see here that is a single span deep beam, which you can see in the figure, which is of more span. You can see from that figure, and you can see this is a 3 span. So you can see here 3 supports. So in the previous figure you can see there is only one span that is present between, single span, whereas if you consider here how many pillars are there, 1 2 3 and 4, total 4 pillars are there. So this is called as a 3 span deep beam. And if you see what is the general thing here, small d is the normal length and capital D is the normal depth, capital D is the effective depth, whereas W is the load and T is the thickness, and you can see here L is the length of thing. So if you take the type of loadings, first one in the case figure, that is the top loading, you can see in the first figure, whereas in the second one that is called as a side loading. Okay, and the same thing if you take at the third figure, that is nothing but a bottom loading. So top load, you can see it is present at the top, whereas next one is the side loading, next one is the bottom loading. So these are the different types of loading in deep beams. Either it may be top loading or side loading or bottom loading. It will be again very depending upon the design considerations which we are following. And you can see here what is the variation of the cracks of deep beams with the top loading as well as the bottom loading. So and if you can see if you take the top loading, we are getting the flexural cracks which is arising from the columns, and you can see it is starting from center point to the utmost point, up to center portion of the beams. Whereas second one, if you take the bottom loading, you will be getting the shear cracks which it will be spreading throughout the beam. You can see with the top loading you are getting the flexural cracks, but whereas with the bottom loading you are getting the shear cracks. So that is the main difference between when you are going for top loading as well as the bottom loading. So again, depending upon the design consideration, it may vary from type of slab as well as type of loading. And you can see here next one is the stress trajectories, and you can see in the case of top loading, so the stress is distributed throughout the beam. You can see here from the from bottom end to the top end the stress is distributed. But whereas in the case of this thing, distribution of theoretical horizontal elastic stresses, so first you can see it is at the midspan, and at 1/4 point at certain portion you can see the compression portion, and at another portion you can see the tension. So at the both the portion, so at midspan, like you are getting also again both the compression of the tension, whereas at the 1/4 point also you are getting both the compression as well as the tension. Okay. So this is the next one is the truss model. So in the case of truss model, you can see here the angle you should maintain it as 68 degrees if the length to height ratio should be less than 1, and otherwise if the length to height ratio is 2, we have to maintain 54 degrees. Whereas second one, you can see next one is the redefined truss model. So here you are getting the WL/4 we are applying at 4 load point, whereas in the previous case we have applied only at 2 points, that's why that is given as WL/2. So here also the angle should be maintained as 15 degrees on one side and 15 degrees on the other side. So this is about our first topic, and just quickly I will be revising the topics from the first one. And coming for the definition of the D beam, the term D beam is defined in ACA code as the member located on one face and supported on the opposite face, so that compression struts can develop between the loads and the supports, and they are having either clear spans equal to or less than 4 times the overall height of the beam, or regions located with concentrated loads with 2h from the face of the supports. And you can see here this is a single span beam throughout the structure from the top to the bottom, which is clearly evident in the figure. Next one, this is the 3 span beam, and you can see we are having total 4 columns, which is at the 2 are present at the end portions, 2 are present at the middle portions. So here you can see we are getting 3 spans in between the slabs. And coming for next one, here in this figure, D is the normal depth and capital D is the effective depth, and whereas L is the length of the beam, and T is the thickness of the beam. So here we are showing what are the different type of loadings in the D beam. First one is the top loading, and second one is the side loading, and third one is the bottom loading. And you can see top loading is given in first one, okay, directly on the top, from the top it will be uploaded, whereas at the sides it will be loading will be given on the either sides of the beam, and next one is the similarly it is the bottom loading. And next one you can see what is the variation of cracking in D beams with the different type of loading. If you take the first figure, that is with top loading, and we are getting the flexural cracks if you are going for applying the top loading. So it is starting from the bottom and it is going up to center portion of the beams, whereas if you go for bottom loading, we will be getting the shear cracks, which it will be spreading throughout the beam. So again, which type of loading is preferable, that is depending upon the type of the design consideration, which we will be seeing in the next slides. And coming for the next is the stress trajectories. So with the application of the top load, if you take the stress trajectories, so the stress trajectories, it will be distributed throughout the slab. You can see from the top portion to the bottom portion, and from this end to that end, the stress is completely distributed onto the beam. And next, if you take the distribution of the theoretical horizontal elastic stresses, so at the midspan you will be getting both the compression as well as tension. Similarly, at 1/4 point also, again you will be getting both the compression as well as the tension zone. Okay, so with this I am ending the session 1. Thank you all.